Okay. Hello everyone. Welcome to the another session of Designing Data Intensive Applications Book Club. Today we are going to discuss about batch processing. So hopefully we will discuss about some of the tools in the Unix that could be used to do batch processing, and then we will look at a very basic fundamental uh, uh, idea for doing batch processing, which is MapReduce. Uh, and we will look at how Hadoop uses MapReduce. uh, and then, yeah. So, and then I was thinking that in last 10 to 15 minutes, we can continue our discussion of looking at these maps and revising one of the previous chapters like we did last time if we have some time left. Okay, so yep, so let's begin. So basically, when we are building any kind of system, we generally build three kind of system. Either it's a online service. So by online service, uh, we are building something for which user is waiting for a response. A user makes a request and he's immediately waiting for a response. So in those services, we have to serve the request as fast as possible, right? Those are online systems. Then a second set of systems are batch processing systems. So batch processing systems are also called offline systems. And in these systems, we basically uh, do processing of large amounts of data. And it usually takes some time to process that large amount of data. And it's offline because basically this is in terms of from a user's point of view, it is not happening when user is making a request. It is something that our systems are doing uh, to for some kind of analytics or for some kind of other process for which the user is not waiting. So that's why in these scenarios we are okay if the process takes more time, but basically we want to crunch large amount of data, we want to crunch large numbers, right? So those are batch processing systems. The third type of systems are stream processing system, which are called near real-time systems, which are like similar to batch processing in the sense that they uh, process some amount of data, some large amount of data, but it's not. So basically, they keep on incrementally uh, processing the data, so that data is not so large, and basically at regular intervals, as the data stream keeps on coming, it keeps on processing the data at some small delay of minutes, right? So basically, these kind of systems, one a very famous use of these kind of systems is for monitoring and alerts, right? That you have a stream processing system that looks at the health of your system continuously, process that data and monitor and alerts you if there is some issue. So that's the basic. So uh, then the chapter in the chapter it is mentioned about Unix tools for batch processing. So how many of you uh, use Linux day to day and have a good understanding of Linux? Because this chapter uh, is like involves some understanding of Linux. Uh, okay, nice. Okay, yeah. I was always using Windows, but from past 1 or 2 months, like I remember that I studied Linux in my college 6 years back, and I revised it a month or two back, and so I found that understanding this part was now very easy after understanding Linux. By the way, I feel that Linux is like such a great operating system if you are a developer. Like for developers, it's so awesome working on Linux. So and so now, like now this part is very interesting. So we will jump into each part slowly one by one, and then I will bring some other points which I think are related to this piece what Martin Tipman is explaining. So, uh, so basically, let's say we have some data. So the example which was taken in this book is, let's say we have logs. Uh, so let's say we have a website and we have logs of who visited a page of that website, right? We have logs of that so that this user visited this page at this time with this IP address, like this we have logs, right? Now you have a big file of logs. Now you are given a task that you need to find out top 5 pages visited for the website, right? So let's say you're given this task. So now this is a batch processing task that you have to process this large amount of data and find out what are the top 5 websites. So there are two ways to do it, right? You can do it in Linux or Unix by running these commands, right? So basically, what so the first command is that you open that log file using cat, right? Then there is this awk command, right? So awk command lets you process a file and match some pattern in the file, and then do and then take a action if that pattern matches on that file. So basically by print 7 we are saying that find the seventh character find the seventh word in each line and print that. So let's assume that in each line the seventh word was the URL of the page visited, right? So then we are taking that seventh word, which is the URL. So this will basically print the URL on each line. Then the sort command will sort those lines. Uh, so now all the same URLs will be together, right? Because they are sorted. Then the next command is unique and -c count. So then we are taking count of unique URLs, right? So now we have taken count of unique URLs. Now we are sorting them in the descending order, right? So -r is reverse, so sorting them in reverse order, and then taking the top 5, right? Head taking top 5. So this will give us top 5 URLs that we want to that the users have visited, top 5 pages, right? So this is how you can do this in Linux, right? Now we will see how you will do a similar thing in a programming language, and then we will discuss which one is better. So like in some programming language, in any programming language like Python, Java, Ruby, or whatever, what you will do to do a similar task, that we will basically create a hash map, right? In that hash map, the key will be the URL and the value will be the count of the URL, right? Then we will open that file again using some file uh, file libraries for that language, and then we will go line by line and we will take the seventh word, which is the URL, right? And then we will add that to the hash map and keep on increasing the count, right? And then the third step we will do is that like we would have to sort the hash map on the based on the values, because values is the count. So we would have to iterate through the hash map, then and sort it based on the values, and then take top 5 uh, keys of the hash map, which will be the top 5 URLs, right? So we'll do something like this in a programming language. So now, which one is better? Anyone wants to tell? Using Linux, like the same thing you have done in Linux, the same thing you can do in a programming language.
I would say if the data set is like manageable on a single machine, the Linux approach is very fast, and you can even code it in like less than 5 minutes.
Yeah.
Whereas this programming language is gonna take time, uh, 10 times more.
So yeah, so let's say that both of the things are happening on a single machine. It's not distributed. So right now we have not jumped into distributed, but you have mentioned that Linux approach is faster. It's 10 times faster. We can all see that, yeah, the code looks much cleaner in Linux. Like you can quickly write this thing. Yeah, but is there a reason that the Linux is faster? It's 10 times faster.
Actually, I wanted to say like development time is like 10 times less than the second option.
Mm-hmm. Yep.
Yeah, and um, this it also depends on like, are you going to like in the second option, are we going to sort by ourselves? Like if the language that we are using, does it has an option to sort a hash map by count and all? Uh,
Mm-hmm.
that things will also come into picture, right? Uh,
Yep.
Whereas in Linux, you don't have to worry about the memory and all. It takes care of all these things in itself. Like,
Yeah. Yeah, agree. So yeah, definitely the like, yeah, you would have to do something here, that either the programming language will not have a directly sort on a hash map, and then you would have to iterate and write some code here, right? Which might be little, yeah, which might take some time to write over here. So that's one thing. But the another important side of this, like uh, that from the compute point of view, from the time it takes to process the data, right? The Linux thing is will be faster, and Linux one has some other advantages as well. So those are the first thing is, so imagine a scenario, so that we're taking a hash map, right? And this hash map uh, are is stored in memory, right? And then we are also sorting. So most programming languages implement sort in memory, right? Now imagine that if you have so many different URLs, although uh, in this example, the generally URLs are not a lot, right? So basically, this URL and count, they can easily come in a hash map. But for some other example where your data will not fit on in the RAM, like the your data is so huge that it will not fit in the RAM, then there is a program. Then there is a problem with programming language, which is the advantage of Linux. So in programming languages, most programming languages implement sort function in memory, right? So you're limited to your data by how much it can fit in memory, right? Whereas the Unix, it automatically like it automatically uses disk as well, and it automatically spills your data on disk, so it can sort much larger data set even if it cannot fit on the memory, right? And then the other thing is that the sort utility in Linux, it also automatically uses multiple CPUs of your computer to parallelize the sort, right? Whereas the programming languages generally don't do it. So these two advantages make this Linux thing much faster. If you're running on a large amount of data, you can see the difference that this will be faster. So if you guys have read the book, so this is what is mentioned in the book. So from this, there is this very interesting question, and I want to know if anyone has done this problem before. It's a very interesting problem. Have you guys heard of external sorting?
Yeah, I heard about external
yeah.
sorting. Yeah.
Yeah. So basically, this here we are talking about this external sorting, right? So basically, Linux kind of implements this sort in external sorting way. So basically, uh, so external, just for everyone to know that external sorting is that, so generally in programming languages, this sorting happens in memory, right? Whereas external sorting is that you are sorting the data which is like, which is so huge that it cannot fit in memory, and so you have to use your disk as well to sort that large amount of data. So how is, can anyone knows what's the algorithm behind external sorting? How does external sorting happens?
So you are saying these Linux commands, they sort of store the data into disk. So say when you call sort is going to pick the output of AW key and store that into some temporary file and then do the sort.
Uh, so so my understanding is that if it needs to use disk, it will use the disk. Like if your data is small enough that it can fit in the memory, then definitely it will use memory to do it, right? Because it's fast. But if your data is big that it cannot fit in memory, then Linux sort will automatically handle that case, that it will use disk space as well to sort the numbers. Whereas the programming languages, they are just limited by how much data can fit in memory.
All
Yeah,
right, so it then becomes a sort of a append-only file, and then you can use these sequential readings to speed up the processing and doing the external sorts when the data is huge.
When the data is huge, yeah.
Cool.
Is that it still bring the data in memory? It's
Yeah,
sorted and then push back to disk, and it
Yeah.
Bring the next batch of data to memory and
yeah, I
sort it.
can add a couple of words on this. They usually call it spill. If we don't have enough memory, yeah, we spill it to disk. Let's say we spill some kind of array to disk, and then we usually use some kind of merge sort algorithm in order to merge already sorted parts.
Yeah, awesome. Yeah, exactly. So this is the example behind external sorting. So let me quickly take 5 minutes and explain like how external sorting works, which is like very interesting. Like I really love this algorithm, and I have also implemented it on my like GitHub when I learned it. So basically, so the problem is this. So basically, let's say your RAM, you have RAM of 4 GB size, right? Let's take this example. And now you have data. Let's say you have simple numbers, which are like, let's say, for 16 GB of numbers, right? Now you have to sort the 16 GB of numbers. How would you sort it? Because if you will read like basically whatever algorithms we have seen, right? Which these programming languages implement, they have to bring the numbers in memory and then sort them. But now you have so much data that it cannot fit in memory. So how would you do it? So basically, like just a brief overview of how the algorithm works is like basically as who has mentioned the algorithm? What's your name? Sorry.
Merge sort, multi-way merge sort.
Yeah. Okay. Yeah. So you use merge sort, right? So basically what you do is that you split this data into small chunks which can fit in your RAM. So let's say you will divide this data into 2 GB, right? So first you will get 2 GB of data. You will sort this 2 GB of data. So now you have 2 GB, 2 GB of data, which is sorted and which you again then write back to the hard disk, right? So now you have these bunch of 2 GB chunks which are sorted, right? And now, so basically now this is another programming question, which I think some of you would have seen this problem. So the problem is that you have bunch of sorted files. Sorry, you have bunch of sorted lists, and then now you have to merge them and sort them and create one list, right? So this problem is same, that you have bunch of these 2 GB files who are sorted among themselves, but overall it's not sorted. So you have to create an overall sorted list. But again, the limitation is that you can bring only 4 GB in memory, right? So a basic simple approach, a very brute force approach, is that for each of this list you will pick one first number, right? So basically, because it's 16 GB of data and each is 2 GB, so you will have these 32 lists like this, right? So you will pick the first number out of all of them. So you will pick 32 numbers, and out of those 32, the one which is smallest, that will be the smallest in all, right? So you can be sure that you are sure that is the smallest number. So you can write that back to the disk, and then from the list, let's say this list has had the smallest number. So from that list, you pick the second number, right? And now compare again these 32 numbers, which one was the smallest. Then you output the smallest now. Then again, you take the next number, right? So like this, you keep on repeating. So basically, like with the simple approach, so basically you always have only 32 numbers in your memory, right? And the number which is sorted, it is already outputted to the disk. So this is basic approach, but it could be improved much more, because basically you could load much more numbers on disk and you could output uh, a, a big chunk of numbers rather than outputting a number one by one, right? Because if you are outputting a number one by one, you're doing a lot of disk reads and writes, which is expensive. So instead of doing disk write for each number, like basically you keep on storing those numbers in memory as they keep on getting sorted. And once like you reach some size, let's say you reach 1 GB of data, then you put it back to disk, that's sorted disk. So this is like basic algorithm. And if someone would have done this problem, then the other thing is that basically to optimize this, that you have to pick the smallest out of 32 numbers, and then a new number would be added. A heap is a more efficient approach, because in heap you basically maintain a min heap. So the smallest number will be at the top of the min heap, right? And so you can just get that in big of 1, and then you have to heapify it, which will take big of log n, and then you again add that new number to the heap, which will also take big of log n. So it will be much faster than if you like use simple array or something to sort these, right? So this, yeah, so this is like a basic algorithm behind this external sorting. So what we are saying is that here, coming back to our discussion, that the sort utility of Linux has taken care of all these things, right? The sort function that programming languages have, they just sort if the numbers can fit in RAM. But the sort utility for Linux, they have taken care of this scenario, that what if the numbers cannot fit in memory, then implement the algorithm which can still sort it, right? So this brings to the point that why this Unix and Linux are such great operating system, and what was the philosophy behind them, why, how they were built. So basically, when the Unix, like 30 years back, when the Unix systems were built, so they had these four philosophies. So the first one was that make each program do one thing well. And if you want to do something else, then rather than modifying that existing code and complicating and doing bunch of stuff which makes spaghetti out of your code, build something fresh and then try to reuse your uh, code, and that's basically build those small components which does one thing really well, right? Then the second thing is that break down big projects into reusable, manageable chunks, right? So basically expect the output of each program to be the input of another, right? The third philosophy was that go behind rapid prototyping and experimentation, that rather than building something ideal, that if you are given a problem, like if you are building something that is ideal and the best, instead of that, quickly prototype and experiment things and see how customers like it or not, and then basically keep on iteratively building it, right? The fourth thing is automation, that basically in your day-to-day programming task, you would have to do some things uh, that that are kind of repetitive and that need some unskilled efforts, right? So take some time to build tools to do those tasks so that those things could be done quickly. And then basically don't be afraid that yes, those some of those tools could be throwaway tools, right? So these 4 points, right? This is the Unix philosophy 30 years back. 30 years back, when the people were building Unix, this was their philosophy. And like, does this sound similar to how we do our jobs these days? Like, does this sound familiar to you guys?
Yeah, and I also have one more question. So as we've seen, right, this is a old style of programming and arranging the software.
Mhm.
But recently, like when I was querying this AWS CloudWatch and Elastic, there also I found like a similar style, the way you wrote like awk, sort, but these not exactly the functions. They have just the different functions, but they also use this pipe kind of a thing, like filter this and apply this, not in all that conditions, and then sort it and all that. So do you
Mhm.
know if it is like using this exact thing at the behind the scenes, or is it like, I mean, have they created their programs in a Unix style, like okay, let's create a binary for sorting the data, let's create a binary for filtering the data, like that?
Yeah, I don't know. So was it their own some, like, what language did you write this thing in it? Right, this is Bash
Yeah.
shell code,
So,
right?
so
So what?
this is
Oh,
Bash. No, I'm talking about, so in AWS,
mhm.
you so they have a system called CloudWatch. CloudWatch is basically your all the logs, the way you mentioned, right? All your web server logs or database logs, all the logs comes into that system. And if you want to query that system, they have a almost similar syntax like this Bash. So if you want to, let's say, read the data, you will just open that log. I mean, it's all on the web page, and then you will say, uh, pipe, like you will say initially, like give me the first and second field, and if the first field is a time and second is a number, then I will say, okay, if the second number is more than this, then field pipe it one more time, and then sort it, and at the end give me the top 10 or top 20. So when you want to query the log in CloudWatch and all, you will use almost similar style to
Oh,
query. As a user, as a UI, they have given like this interface.
yeah. I don't know, like, behind the scenes, what are they doing? I like, it could be either like some programming language on which they have added this syntax sugar, right, which
Yeah.
looks similar to Unix, or it could be, yeah, they could be Unix, they could be using Unix or something to actually implement it. I don't know. Does anyone else knows what is CloudWatch doing behind the scenes?
Probably the syntax itself. The syntax might be similar to the Linux, but I mean, if you take AWS or Elasticsearch, generally you don't have a single machine where the data will be stored. If the data is, I mean, but they might be taking the principles from here. Like, I mean, mm, when you're doing an arc, you can actually, I mean, this might be a process, and that is actually sending to uh, output to another process. I mean, the underlying principle might be the same, but it may not be a actual Linux or something like that.
Yeah, yeah. Right.
For
Yeah.
the, for the pipe, I think for the pipe, look at it, we might think it, okay, all the process had to be done by the first pipe, and then the output gonna go to second pipe, and so on, right? But in some case, it's like a stream, the process online, on the fly. I mean, the input go in the first pipe and go out to the second pipe. So it's like a stream. It's not like, you complete the first pipe and then you done the second pipe.
Yeah.
Yeah, as for me, pipe is a kind of function. Yeah, we have a function. So in function, we have input and output. And pipe let us composite to make a composition of function. Let's say that each command is a function. It takes input and produce output. And pipe lets us just do composition of function.
Yep, right.
Yeah, but beside the function, it also have kind of like, the thread or something to keep it going, right? Because if a function want to receive the input and they're done with that function, and that process terminate. But this one, it keep waiting for input. That's different, right?
Oh yeah, you are talking that it's not a greedy execution. Yeah, it's
like a
right
stream. It keep
quiet.
waiting. It keep waiting. If one is done with the function, and then it go back waiting for the next input.
Yeah.
Unless like the input, contain the token or something, say terminate, and then the function terminate.
Yeah, I agree. Yeah. So it's work line by line or something like this.
Yeah, right. A while loop.
Okay. So moving on. So we have discussed that how the Unix approach has been implemented in a better way, right? So basically, the great Unix philosophy which we discussed, this is similar to what we call agile development today, right? Agile and DevOps, that build things fast, iteratively build things, right? And break down the project into smaller chunks, which could be which are reusable and which does one thing really well, right? So all these things. So now moving on to this, again, this first piece. So basically the discussion which is happening, that so in Unix, like, there is this philosophy that you can use these pipes to take input of one process and then output it to the other, right? So basically, and this thing could be done with various other lot of things, right? So how does actually, if Linux has to support this, then they have to build the underlying system in such a way that the output of one program is compatible with the input of another program, right? Because if they both are compatible, then only it could be fed as the input to the other command, right? So now how does Unix takes care of having a uniform interface so that the inputs and outputs of various programs can be linked with each other and they are compatible with each other. So the answer to that is files. In Linux, everything is files, right? So if you will see, if you want to see what are the processes running on your system, it's a file. You go to /proc. In that, you will see the files of all the processes running with the process ID, right? So basically, using this very simple idea that make everything file, lot of things become compatible with each other, because now you are just reading files is those bytes of data. So you are just reading those bytes of data. And so that makes a lot of things compatible with each other, right? Then the other piece was that like Unix also has this thing using this pipe operators to, which acts as a wiring thing, that you are wiring your things together and these commands are your logic, right? So this separation of wiring the things together and then writing your logic simplifies things a lot. Imagine like if you would have to do something like this in a imperative language where you would have to specify these things on your own one by one, then it becomes a little more complex and your code becomes mixed up with your actual logic and your wiring up, whatever wiring up you're doing. Like if you are doing, if the same thing we wrote in this programming language, like everything was mixed up, right? There was no separation between the things we are using as input from one, output of another, and then using that separation was not very clear. Whereas in Linux it was very clear because of this use of these pipe operators, which act as the tools to connect your input output, and then these commands, which are those commands that are like kind of the commands in declarative languages where you specify a command and they will do those things for you, right?
So let's say if it use the file from output, of one function or one. Okay, maybe first, want to clarify. Look at the in Unix command. Each of that command is run in separate process. Is that right? Like cat is run in one process, arg run in another process, and sort is another process.
I don't know. I don't have answer to that. Are they the same process or are they happening as part of one process?
Yeah, they are from different process. Each of these command will be running in new process.
Okay. So we have different process, and then the output of one file become the input of another file. But let's say the input of another process. But how the second process know where the delimiter? How the second process interpret the file structure of the input. How does it know where the next field is?
So by default, these shells have, they call it as an input file separator variable, call it as IFS. And by default, it's a new line. So by default, without, if you just run this command, it will assume that new line is a field separator. But if you are writing, like say example for an awk program and you want to use a different input file separator, IFS, then you will set your, like you can set anything you want, any character you want.
Okay. Okay, thank you.
Okay, so yeah. Yeah, so basically these were the things mentioned about Linux / Unix, which makes it like really simple to write complex jobs, which could be done easily. And just one thing, so in this case, we are not outputting files and then these are like taking input of those files. Here, these processes are just sending input and output to each other. But we could also use files. Basically, we could, if we have to run a big batch kind of a process, then we could also at some step save the output to a file. And the advantage of that is that now that part of your computation is saved in a file, so you don't have to repeat it again, right? In this, you have saved nothing on your disk on a file. So if you have to do it again, you have to compute this thing again. So the other option is that if you want, you can save it to the file and then reuse that part, right? So that is another thing that you and also when you are using files for input and output, so those files are treated as immutable, so you don't modify the input files, so which is great to do the experimentation, because you don't have to worry about modifying your original data, right? Because you want to keep your original data intact. So that's the other part, right? So you can use the files are immutable, and then you can use output of a program to save it to a file, which can be later used as the input in the next stage. So now, like whatever we have discussed, these things in Unix, they all happen on a single machine. There is nothing distributed about it. And that's the big disadvantage of these Unix tools, that they are built, all of these Unix tools, they are built for a single machine. Like they have not been built for distributed machines. And that's where MapReduce and Hadoop comes in. So these are the frameworks which have been built if you want to do distributed computation, right? So moving on to them.
One
Yeah.
question about the sorting. So are you saying that like when we do like sorting to the file, those file, then Linux, they don't know if they can do it in parallel. They just sort it one by one and then merge them, right? Only one.
So
it's not doing it in parallel.
No, Linux is doing it in parallel, but on a single machine, like how many CPU cores you have. So they will try to parallelize on that single machine CPU core, but it will not try to parallelize, like you cannot use it to distribute among multiple machines and then parallelize it.
Okay.
Yeah. So yeah. So now coming to MapReduce and distributed file system. So now, like understanding this Unix philosophy, like if we will see, MapReduce is in some ways similar to Unix. It's just like now distributing this across multiple machines, across thousands of machines, rather than doing this thing. So the external sort algorithm that we have discussed, right, on a single machine, that your data was living on a hard disk of 16 GB and then you had only RAM of 4 GB, you have to sort. The same algorithm could also be implemented on distributed machines. Basically, you have a distributed file system where you have large amounts of data, right? And then, so basically each of the machines is reading some data, and individually this one machine is sorting some data, another machine is sorting some data individually, and then we are merging the data, right? So the same algorithm could be applied to distributed machines as well, right? So yeah, so we'll see that how, like, so the MapReduce and Hadoop, it's also similar in this sense, right? That it takes some of those learnings from this Unix and then distribute it across multiple machines, right? So generally, like Unix tools, they use, like, if you are not specifying the input and output, then the standard is std in is your input and std out is your output. So std in is your keyboard input and std out is your screen, right? Or you can specify files, then those files will be input and the files will be output, right? In MapReduce, you use distributed file system as your input and output. So you will have a distributed file system and that will act as your input and output. So before we jump into this MapReduce, like let's understand briefly about the distributed file system, right? Because it is that fundamental part of these systems which is used as input and output for these systems, right? So what is this distributed file system? So the two very famous distributed file system papers are GFS and Hdfs. So basically Hdfs is an open source implementation of GFS, Google File System. So basically was this the diagram? Yeah, right. So basically Hdfs is a shared nothing. Hdfs is based on shared nothing principle. Does anyone want to explain what is the meaning of shared nothing? So basically, the distributed systems could be built in few ways. So one of them is shared nothing. So shared nothing is that each of the machine is independent and they don't share anything, right? Whereas like there could be other kind of systems where you are like using a file, like a file on a network, like a hard disk on a network, and that same hard disk is shared between multiple machines, right? Those could also be like you have a common storage system and that is accessible through network and all of them are accessing that same, so that component is shared, right? So there are systems like that, but this is based on the shared nothing, that each machine has its own storage and each machine has its independent hardware components and they don't share those independent, they are just connected via network and they talk to each other via network, right? So that is shared nothing principle. So this basic architecture of HDFS is like this. So you have a name node, basically it kind of acts like a master node, and then you have data nodes, right? So these data nodes are running a daemon process, each of these data nodes, and basically this daemon process gives the access of the file system on this machine to uh, any other machine who wants to access it. So if some machine wants to access the file system of data node 1, then they will talk to the daemon process and daemon process will give the access of the file system to, let's say, third node if node 3 is asking for it. So now basically how do you store a large amount of data in this distributed file system is that you partition the files and then you replicate those files and then you store those files in these data nodes 1, 2, 3, 4, 5. And the name node, it keeps the track of which node has which chunk of that file, right? So basically it is like it has a kind of overall view of if you want to look for a file, which node you should go to get that file. So now if a client, he wants to get a file, first he would have to talk to the name node, right? So the name node will then, so it will talk to the name node that I want to get this file. So the name node will return that, hey, the file of which you're looking for, it is on data node 4, right? And it will return the IP address of that node. So then the client could then directly connect it to that node 4 and start getting the data from node 4.
So,
Right? So
so the client, you were saying that a file will partition into 5 parts, right? And each part will store at each data node, right? And then the client, how does the client know? I mean, the client only know the file name. Then how does it know, like, what part the name node know what part they have to go to?
So the name node will return that information if your file is splitted among multiple nodes. Then the name node. So if it's so either there could be two ways to do this, and I exactly don't know how Hdfs is doing is. So one thing, one way to implement this could be that the name node is, so let's say if file is split into 3 nodes, right? So it is partitioned in 1, 2, 3. And now if a client is looking for a file which is now split in 1, 2, 3, so basically it can give like one of the partitions, it can return you one of the partitions. So you talk to that partition, and then these partitions talk among each other. Like they also have this information of like where the other pieces of those files are, and then they like, and then you just talk to one of them, so it talks to the other and return you the files. Or the
So
other could be that it is returning like 1, 2, 3 all the nodes, and then the client connects with them. Yeah.
So, so data nodes don't like that particular file chunk which is on machine 1 to 3. Those chunks do not know where the other part of the chunk is. The name node will store all that information.
Okay.
So if
So
you want to teach a file, it will say, okay, go on to this block, and this block.
okay. So yeah, so basically the name node will return all these 1, 2, 3 to the client, that it is like some chunk is stored in data node 1, some in 2, some in 3, and then the client has to connect to all 3 of them to get the data, right?
Yeah, so a name node knows like which blocks make the file, and it also knows where are these blocks because it's a replicated file, right? So that also is stored.
Yeah. So, but then in this case, the like if I want to get the entire file, the client has to uh, like do the logic of parallelizing it. So basically, if I want to read that file, uh, and to make the process fast, I could like read it from multiple nodes, right? So do I have, as a client, have to write that logic?
So let's say if you are doing just a cat, so Hadoop provides that utility, so you don't have to worry about that. But what you are saying, it's that's what the MapReduce does, right? So when you submit a program to the resource manager, distributing it and running it wherever the data is, that is taken care of by the framework.
Okay, right. Okay, yeah. So, right.
If I recall correctly, in that how it actually happened in the GFS. So the client library take care that it make a request to this the server and get the size, and then it make a request that a particular offset, where is that, and then it gets that information, and in parallel it actually download those chunks from those whatever they call it, the client machine or no chunk server.
Yeah. So, yeah. So, yeah, he's also saying the same thing, but what he's saying is that MapReduce provides you a wrapper around it. So now in this case, MapReduce is acting as a client to Hdfs, but that's the wrapper that is doing all this work. That whatever you have mentioned, that it goes to all those nodes and parallelly get that data. And like Hadoop, right? Here we are talking about Hadoop. So Hadoop uses Hdfs. So Hadoop is that framework on top of it. Hadoop is the client which does that. So yeah.
There is an analogy here. I mean, the name So when you're trying to write it to the Hdfs, the write also happens like Linux. The piping and these all are arranged by the name node itself. So when you try to write a file, the name node actually finds, depends upon the replication factor. It selects the nodes and it creates the pipes. So when you write it to one node, the initial nodes take care of writing it to other nodes, and these are like in a pipeline fashion.
Okay. Yeah. So like another thing is that these files generally they're like 128. So the files are large files are split into 128 MB of chunks and then partitioned across multiple machines, right? So this was our distributed file system, right, where we can store large amount of data on commodity hardware and split it across various machines and replicate it, right? Now using this, now we will see how MapReduce takes this data as input or output and then do the computation, whatever computation you want to do on top of it, how will it do that computation? So this is like a basic diagram of like how MapReduce job management will work. So let's say as a client, you will write your MapReduce job, and we will talk more about it, what exactly a MapReduce job is, like what are the various components. I think let's first discuss that first, like what exactly this MapReduce is. Then we will see how we submit this MapReduce job to a MapReduce job tracker, right? Which will then access this Hdfs kind of a distributed file system and submit that job to those nodes, which will do the processing and computation of uh, of on the data which you have, right? So yeah, so coming to MapReduce. So basically, MapReduce has two components, mapper and reducer, right? But actually, like if you look at this example, so how MapReduce will work is, so basically, let's say I have three machines, right? And I have some text on them, right? And my goal is that I want to get a count of each word, right? So basically, I have a large file which has text, and so that file is now split on three machines. So I was using a distributed file system to split that file and store them on three machines. And now the task is I want to get the overall count of each word, right? So I would have to write two functions in MapReduce, a mapper and a reducer. So what mapper will be doing is that it will create a key value pair. So out of my data set, it will find out what is the key and if there is any associated value with that key, and it will then separate out those key value pairs from my input data and output those key value pairs. So in this example, basically in my mapper, I would be saying that like split this text into words, and then the key is the word and the value is the count of that word. So this will be my mapper code. So, and the output will look something like this, that for each word, it will give me the count. So like I has a count of 2, has a count of 2, and like this, right? So I got this output of key value pair on each machine, right? The second thing is I would be writing a reducer. So the task of reducer would be that now you have these key value pairs and you have to combine them. What is your logic of combining them? So in our case, the logic is that we have to add, right? So basically we have to add the count from all the files and return the sum of the frequency, right? The So a middle step which happens, which is called shuffle step, it is like implemented by MapReduce framework. So you don't have to do it, but basically what this shuffle is doing is it is bringing the data with the same key on one machine. So right now, the key with the I, it has some component on machine one, some component on machine two, right? So shuffle will bring them all to one machine. So the key starting with I, let's say, brought it to this one machine. So now we have this key I, and the values were 2 and 2 from these two machines, right? So similarly, the data with the same key now lives on one machine. So now the job of reducer is simple. Now because the data is on one machine, so now the reducer has to just add the values of each key, right? Whatever logic we have written. So in this case, we have written the logic that add sum the values. So then the reducer will sum the values, and basically now you have got the final output, right? So each, what is the frequency of each word? So this is your basic, like how MapReduce works. So it has this map, shuffle, and reduce. As a user, you specify MapReduce. Shuffle is like internally handled by the framework, and yeah, so that's your MapReduce. So yeah, any questions?
Yeah, what the logic of the shuffle? How does it know, like, you bring the same key to a same, I mean, yeah, how you bring the same key to the same machine?
Yeah, so internally, how like MapReducer framework would be doing it is that it associates uh, each key with, like, it's like it basically takes the hash and it associates like a set of keys with each machine, right? So basically, like, I have these set of keys, right? I can take a hash and say that these keys have to be split on these three machines. So a simple problem that you have a set of key value pairs and you have to split it on few machines. So the way you could do is you can take a hash, and then based on that hash value, you can assign it to that machine. So similar thing is what this MapReduce is doing. So let's say the hash of I came out to be some value which is associated to machine one. So then now each of the mappers, its job is that process the data, and whoever is the owner of that key, give that data to that key. So the owner of I, after calculating the hash, is machine one. So everyone, after they have computed the value of the key, they will assign it to the owner of that node.
And one more thing, like, so whenever we have to write a MapReduce job, we have an option, like we will implement the map interface, as well as we will implement the reduce interface. But while running the job, we also have an option, like how many reducers you want to run. Because let's say you want to do a global sort, like give me everything in a one file. In that case, you will say like, okay, I want to sort it by with one reducer or multiple reducers. So the number of mappers is not controllable because it depends on the input split, but the reducers is. And when we see the shuffle phase, right, so that's where the lot of heavy lifting by Hadoop is done. Like when you run a map job, it does not just like output the keys as it has written it. It puts them in a ring buffer, and it then sorts them. Then we also have an option to override the partitioner and combiner. So the keys are like, when we put it in a shuffle phase, it's like those are like sorted
Yeah, yeah.
to make the reducer's job very easy and everyone. So the file from the map one whatever is the output of the map one will be dropped on, let's say there are 3 reducers, it will be dropped on all 3, because we don't know which keys who is going to define. So it's a mass, you can say IO transfer happens, like the network gets really busy because all the files go everywhere, and it generally does this in a chunk of 100 MB. But there is a like it does a lot of things in shuffle to optimize our code.
So your point of having multiple reducer, so in this scenario also, like each machine is running a reducer, right? So what exactly do you mean by multiple reducers?
So reduce, I wanted to say is like reducers, you can configure how many reducers you want. So it also depends on the data size. So let's say we are sorting, right? And we are sorting like a trillion numbers. So in that case, one reducer won't work good, right? It's going to slow down a lot. So in that case, you would
By
say,
one
okay,
reducer, you mean like multiple of these reducer jobs running on
yeah,
each machine, or just like one reducer running on one machine?
yeah, these are like multiple jobs total. Like in this picture, there are 3 reducer jobs running. Like our same code is being run on these 3.
Three, right? Okay,
Yeah.
okay. So you can say you can submit multiple reducer jobs on each machine, and
Yeah,
then those multiple. Okay.
so it's not on each machine. It is like on a whole job level. You can specify like how many reducers I want to run.
Okay.
And more the bigger your job is, you want to have more reducers. And as you also can easily see here, right, sometimes there is a skew happens, right? Like the one key that went to a reduce machine number 3 was so huge that the first 2 got finished and the third one kept on running. So basically it's like running the jobs in serially. So to handle that, they also give us an option to how do you want to partition the data. So we have to implement a custom partitioner so that these things do not happen.
Yeah. Yeah. Yeah.
if if I want to, like right now the reduce data, but it reside in 3 machine, right? And what if I want a single file that contain all of that data? Is that an extra process I need to do?
So you can always access this data, right? So internally, your distributed file system has stored the data splitted on multiple machines, but as a user, like this part is abstracted out from you. As a user, if you want to get the whole file, you will always get the whole file. This is how internally our distributed file system is storing these files.
So those reduced file was there written to the node, and if I need it, the client needed, they had to go and, let's say the client wants to have a single file contain all the data, then they have to read each machine. But is that a temporary file, or it's gonna save there for a while?
I'm sorry, what?
Is that a temporary file, or it's gonna, stay there for a while?
So no, this is the output, right? This is your output, and now if like you would be storing your the fundamental input and output of MapReduce is distributed file system. So your overall data was stored in a distributed file system, and your output is also now stored in a distributed file system. And so now these are files, these are output files stored on your machines, right? And now if you want, as a user, if you want to get this data, you will talk to this MapReduce Hadoop framework, and it will do the job of getting the data from various clients and giving you as one file.
And only those the files that came out in the map and shuffle phase, right? Like I:2 and then in the shuffle phase, those are temporary, like
Yeah.
they just go away, but the output is permanent, like stored in a location.
Okay. And there's probably some notification for the client that say the whole job have been done, right?
Yeah. Yeah. So again, that would be handled by the framework that it will, yeah, I mean, I have not exactly used Hadoop, but
Yeah,
I'm assuming that
you are
it would
right.
give some notifications. Yeah.
Yeah, it's like, so there are two interfaces, like your job will know programmatically, as well as the Hadoop also gives us a web UI. In that web UI, you can see, like here, you can see that your one job has been divided into the three little jobs, right? So you can also see how many maps are running, how many reducers are running, what are their completion status. Everything can be seen on a web UI.
Okay. Yeah. Yeah. So now this was like how MapReduce happens. So now, like, let's see the job management. So basically how the job management would be happening. So as a client, you would be writing your that map reduce function, right? A mapper function and a reducer function in some code. So then that jar file, let's say it was a Java code, it's a jar file. So you will submit that jar file to the job tracker. So now job tracker, like it is this part of Hadoop system. It knows where the data is, right? So it will submit, it will give this map or jar file to all of these nodes. And like it will basically, it's your code, right? So basically your code would be like maximum 50 or 100 MB, right? It's like you can write a lot of code in that much. So it will copy that jar file to all of these nodes, and then there is a process running on each of these nodes which will execute this code on the data which resides on this node, and then the same process which we discussed. So then it will be in a distributed file system. So this is a distributed file system. So it is executing this code on the distributed file system as an input, and then it is putting the data as the output. And then again, it has outputted the data to the distributed file system. So one thing which they say about like this MapReduce, right, that your computation happens closer to the data. So basically all your computation is happening where your data lives, right? And that is true, but also if we see the shuffle phase, right? In shuffle phase, we're actually moving lot of data. So although we are saying that we're keeping things local and we are doing computation locally, we want to reduce the movement of data in the network, right? We want to do the things locally, but also there is this other part to it that because of the shuffle phase, there could be a lot of movements of data between various nodes. Yeah, so I think that was about this Hadoop. So now the next part is like looking at various scenarios where various complicated scenarios in MapReduce, like uh, the hotspot scenario, right? That what if the thing which we have discussed, what if one of your keys is really hot, it has lots of data, right? Which could not probably fit on a machine of that key. Or like if you want to do joins between various nodes, right? Between your data. So how do you do joins, right? So those kind of things. And I think that we should probably take up in next class. So yeah, so I think let's wrap up this part. So are there any other questions or are there any other things? So one thing one thing is that like these days we don't actually write these MapReduce functions, right? We use these frameworks like Hive and all, in which we write these SQL like queries, and these frameworks convert your SQL query into the MapReduce function. So you are just writing you don't have to you don't have to write that imperative code of MapReduce by yourself. You're writing it in a declarative way in SQL like language, and then the Hive framework will take care of like looking at your SQL query and splitting it into MapReduce function.
Normally, how long would the MapReduce take to complete the job? Is there a recommendation time frame?
No, it depends on your data, right? How much data is it and what your computation is. So, and like various other factors, like how the data was partitioned, how the data was splitted, like, and basically how many nodes your data has been parallelized to. And still, like, there could be some scenarios where you could have tail latencies where one node is taking a lot of time to compute, and so you have to wait for that to overall complete your job. So yeah,
Once it finishes the reduce function, whether that file will be modified or the input file, or it will be as is. We
no
can store only those cache result and it will keep on popping whenever we're querying.
So the fundamental thing about these batch processing thing is that you should not modify your input. So your input should be treated as immutable. So the output will be new files. So like think of this scenario, right? That you have your raw data and you want to do batch processing on it. So you don't want to modify those logs, right? Those logs are very valuable because what if you have written some wrong MapReduce function, and now if that MapReduce function is modifying your input files, then you have lost your original input, right? So your input is always treated as immutable. You write the function, you get a new output, so that if, let's say, you have some bug in your code or any other problem, right, you can rerun your job, you can correct your code, you can rerun your job, you have your input data saved.
Do completely again, or it can do the caching thing, or how it works?
Cache, what's your question?
Now we did one time processing. Now we changed one of the file. We added one of the string. Now how this MapReduce framework will help us to compute the less size, or whether it does completely new task again from starting, or
Yeah, I think MapReduce does not do this kind of caching, but I don't know if these frameworks which are built on top of MapReduce, they do some optimizations like that. Does anyone has any ideas?
So no, the MapReduce do not do like caching, but what we can do is the same thing. Like we can. So let's say we are computing some results every day, and we have the results till yesterday. So instead of running the MapReduce job on the whole 1 year worth of data, what we can do is we can just run the MapReduce job on the output of yesterday plus the files that got created today. So it's like you have to do all those things. The MapReduce do not cache or anything. If you give it the job again, it's gonna run the whole big thing again.
Yeah.
then
So
when we compute yesterday result and today one file got modified, then on the time but system because previously we are dividing, like consider machine 2 got reduced, then basically this is again all kind of a the processing, right? Like let's take machine 2, machine 3 got modified one file. Then how we are going to kind of this put this caching in the MapReduce function?
So there is no modification. The file system is read only.
So
It's like,
it's used for logs and all, and so you don't modify your logs, right? You keep on adding the data. So
Yeah. No, my point was like, now we got two files are user updated with the two new information from yesterday. Now, because now previously we used to do map function in all the machines and afterwards shuffle, and now we need to do only in the machine 1 and 3. Let's take machine 1 and 3 only. We need to update these job. How we'll be handling that kind of scenarios?
so there is no way to handle that scenario. But what, like for example, you can create a whole database on Hdfs and MapReduce. Like the Hive is itself a database, and people there, then they like partition the data the way you partition the data. Like you can partition based on the creation date, or you can partition it based on the updation date, and then your job will only run on those partitions. So partition in the sense I'm talking about database partitions. So, but whatever use case that we are talking, like if a file that we have worked on yesterday, there is some modifications to it, and how we can take an example of that cache, that is not possible, at least in the MapReduce framework.
So that means that have to take care by the client.
yeah.
And the MapReduce, it automatically handle fault tolerance and disaster recovery.
Yeah,
Is it?
yeah, it does. So basically, so now this MapReduce framework will be taking care of it, that it has this job management piece, right? It has submitted the jobs. So now if one of your machine is dead, uh, it has this information that where is the other replica of data. So either it will try to submit the job on the same machine, or if the machine is dead, it will try to run it on the replica where the replica of data is,
By rerun the process.
by rerunning on that. Yeah.
Okay.
Okay, so I think
Other one is like how these all data will be synced together between these different tasks. Like we have one, like how the syncing mechanism works here.
so one of the great, so first if we look at the basic MapReduce algorithm which we discussed, right? So you see that basically overall there was no syncing as such. Each one of them can operate and work independently, right? So the algorithm which we saw, each machine, it has to do the job on the data for what exists on myself, on the machine itself, right? It does not have to care about the data existing on other machines. So if a task is given to me, a mapper function, I just need to care about the data that I have. So you don't need to sync and talk to other machines. You just need to handle the data that you have. And then the shuffle piece, which is handled by the framework, the shuffle is bringing the data which is with the same key to the same node. Again, the reason is so that now the reducer, it now has to only do the reduce job on the data that exists on the node, so that it does not have to talk to other nodes. So that's why, like, to answer your question, like the nodes don't sync among each other. They don't have to talk to each other.
Yeah, a lot of work being done by the shuffle.
Like here, when it is shuffling, right? How it will know the data? Like once we have shuffled the I, I'm asking from machine 2 and machine 3. I got the data from shuffling the hash stuff. Now I need to, now again, similarly, the machine 2 also will be doing, it can also pick I, right? When it is common, how they will know I should not do I.
So let's take a simple algorithm. So let's say, so you have 3 machines, right? And now you have to split the keys among 3 machines. So let's say what I will do is, whatever is the ASCII value of I will do %3 on that. So the ASCII value of I is, it would be something like 72 or 73, right? So %3 will give me either 0, 1 or 2, right? So definitely it will give me one value. So based on that percentage, let's say I assign, so the value was %3 was, let's say 0, right? So then that means I will assign it to this first machine. So now if this logic is fixed, right, whoever machine will compute it, they all know that it is the machine once who has to process this key, right? So basically that's how, using that fixed hash indexing algorithm, they know that this is the node which has to process the data, and so there is no confusion.
Okay.
Got it. So I think we are out of time. It's 9. So yeah, let's continue this discussion next Saturday. Thank you, everyone.
Thank you, Abhishek. We don't have a Saturday session for system design, right?
Yeah, looks like we don't have any session today anymore. Yeah, Asim posted that message.
Okay. All right, guys. Have a nice day. Bye.
Sorry, can someone correct the schedule on the reminders, please? Possible?
We don't have the permission to correct that.
Oh, so is there someone that we can contact?
I don't know. Yeah, maybe you can refer to Vivek.
Okay. Yeah, sure. Okay.
So we don't have session today. So right now I'm the host and I'm disconnecting. And I think as soon as I'll disconnect, this call will get disconnected. So yeah. So see you all next time. Bye.
Bye-bye.
So Annie is asking, so we don't have system design discussion today. That's what Asim has posted on the Discord channel.
Okay, what did I miss? I'm sorry. I think you met earlier today, right?
So we have a book club session from 7:30 to
Did you do book
9.
club or what?
Yeah, it's a book club. So that was from
Which did you do? Which book? Sorry, could you tell me what?
Yeah, the book is
You did?
Designing Data Intensive Applications.
Okay. Okay. Thank you. Thank you.